Okay, hi, hello. This is Jonathan. This is very unscripted content, but today I just really wanted to go over some findings that not just myself but my team at work has had regarding linking in Rust. So, linking has basically been a real royal pain in the tail for us on our project. So I just kind of wanted to document some of our findings, what we've learned about it, what I've learned about it, just kind of messing around with dynamic linking and static linking in Rust in various different ways, and talk a little bit about some of the challenges we've faced and at least some solutions to those issues, or at least some answers to the questions that we have or have had. But anyway, we're going to be starting with a little Nix shell here, which just has cargo and Rust installed. I'm not going to explain Nix. This is not the Nix talk, so just all you have to know is that I have cargo and Rust C. And essentially what we're going to do is we're going to explore various scenarios that I've put together in this little linking playground that I've created here. So if I hit ls here, you can see that I have various different scenarios here. We've got the rlib, static lib, we also have the c dilib and regular dilib. So I'm going to start with the rlib first. So if we come to rlib test, you can see that inside of rlib test there's two directories. There's the rlib bin and there's rlib lib. So what this setup is basically showing is that rlib lib is the library project, so it's going to generate an rlib library, and in rlib bin we're going to be using that rlib that was generated by rlib lib. So that's just corresponding to, you know, like cargo new dash dash lib and cargo new dash dash bin. So we've got an executable binary on one side and we have the library on the other side. So let's start by looking at the library. And by the way, a lot of this stuff is in, I think it was PNK Felix's blog. He's talked a little bit about linking in Rust. And so some of this stuff is already covered there, but essentially, in those examples, that was just kind of using Rust C raw. Here I'm actually using cargo, so you can kind of see what it's like in a slightly more realistic scenario, because you know we're using cargo at work, and I think most people who write Rust projects are probably using cargo. So if we look at the cargo.toml, you can see that. By the way, right now I'm using edition 2021. I'm on a slightly older branch. I don't want to switch to the unstable Nix channel, so I'm not going to do that right now, but you're going to see some code differences later. And by the way, because I'm on NixOS, I'm obviously running on a Linux system. That's going to be important later. So here, the only thing I've really added is this lib section to my cargo toml, and I've set the crate type to rlib. So if you don't know what an rlib is, basically that's just what cargo usually will compile, or the Rusty compiler will usually compile your libraries to. And so there's metadata contained in rlib files that the Rust compiler can look at to know, like, oh, that's a Rust dependency, and then it knows how to, statically link it into your project. So this is sort of Rust's proprietary library format. So we're going to try this static lib instead a little bit later, but I just want to show right now that this is the crate type that I'm using. So if we do a cargo build, I did actually run the cargo build earlier, so we can actually do a cargo clean here to delete the target directory. But if we do cargo build, it might take a little bit here. It should be relatively short. Actually, I should show the source code as well. I'm jumping ahead a little bit here. If we look at the source code, it's basically just the source code that gets generated when you call cargo new from the command line. So if you do cargo new -- lib, this is the code that gets generated in that base project. So we have an add function, it just takes two numbers and then adds them together and returns that result. And if we look in target debug, we'll see that we indeed have an rlib here. So this is the output. And so if we come over to rlib bin, so rlib bin basically is your standard hello world project, except this is actually just importing rlib, it's importing that add function that was defined there, and then we just call it. So if we run this, we'll see that it prints a sum 3 because we're adding 1 and 2. So that's just showing that we can call into that and that works. We can look at the target/debug folder here, and we'll see that rlib bin here is our binary, right? So now if I decide to, say, change this to a different form, actually, hang on. One thing I want to show off is that here we actually add a dependency in the cargo.toml. So we have rlib lib here, and I'm just pointing at the rlib lib folder. So it has to point to a folder that contains the actual manifest file, the cargo.toml. When you're just using Rust C raw, you don't have to do this sort of thing. There's some other flags that you can use. I'm not going to show off how to do that. This is just how you would use it through Cargo. Again, you can check out PNK Felix's blog if you want to see how that's done. But essentially, if we come to our lib here, and we edit cargo toml again, and let's try giving this a static lib instead. So static lib, we'll talk about that in a bit, but that's just a different library format. And so the way that's linked in is a little bit different. And if we try to go back to rlib bin, we can do a cargo run here, and we're going to see that we no longer have access to rlib lib, and that's because we've changed the crate type. So this is just kind of here to show that you need to actually change it to an rlib or a dilib if you want to actually be able to link to that through this method, through cargo, right? This is the Rust recognized way of linking other Rust libraries or other Rust code. So that's one thing that I wanted to show off. Another thing that I think is kind of interesting to show here is if we look at the lib, so let's come over here and look at the lib. That's at target debug. So if we do an ls-l here, we can look at the size of each file, and this .rlib file is here. We can see here it's 7,226 bytes. So if we just go back here and we change the cargo toml to use something a little bit different here. So let's say we're going to use what was it again? We're going to add rlib, and we're also going to use static lib. So we're going to have both of those there. And we're going to do a cargo clean. So remember, this was the rlib file. This was the size of the rlib file. And if we do a cargo build again, now if we go and look at that, what's interesting about this is that the file size actually increased. So it went from 7226 to 7642. Now, this is a pretty marginal increase in this case. You also notice that the .a file, the static library that gets generated, is actually way larger. We'll talk about that in a bit. But what you should notice is that this is actually a lot larger than, or not a lot larger than, but it is larger than when we only specified the rlib. And that's a little bit weird. And this is something that we found on our project. It was a lot more pronounced there. The size difference was a bit more considerable, but it was a little bit odd. And so we decided to look into that. And if I just hop over to Firefox here, we can actually see that there is actually an issue talking about this. And apparently some incremental compilation stages, the compiler tries to share those stages between different generated artifacts. And so when it tries to generate an rlib and also a static lib, it tries to reuse some of these steps. And sometimes the steps can be very large. So that, while that might reduce the amount of work done by the compiler overall, it does mean that our binaries end up being a bit larger as a result. And you can also see that there's a related issue here where they talk about how LTO is ignored for all crate types when building multiple crate types, and one crate type doesn't support it. So yeah, that's another related issue to this. Definitely worth looking into if you're using multiple crate types. There's some workarounds. I think they actually mentioned one down here. Like you can actually explicitly set the crate type using cargo rust C like this, and then you can do individual builds. So if you're worried about your library sizes, then yeah, this is something that you should be aware of if you're using multiple crate types. Alright, so that's everything I want to talk about here with the rlib. Let's go to the dilib next. So this is regular dilib, not C dilib. There's actually a pretty big difference there because the regular dilib is the dynamically linked Rust library. So it's something that contains metadata that the compiler can actually process when linking all the dependencies. So here we got a pretty similar looking setup. I can show that off here. It's the same code as what we saw in the rlib or static setup. And if we just run cargo build here, then we should be able to reference that from dilib bin. Once again, it's the same setup over here. So this code is exactly the same. We're adding 1 and 2 together. The cargo.toml also looks pretty similar, right? So we're pointing at the dilib lib dependency, and we can run that pretty much exactly the same way. So PMK Felix's blog post talks about this particular format in greater detail. But essentially, you kind of have to be careful with these dynamic libraries for Rust, because if you compile the dilib with a different version of the Rust compiler than the binary, then you might run into some compatibility issues, and then stuff will go all wonky. It might not even load properly. So something to be aware of when you're working with the dilib here. So that's all I really want to say about that. We aren't really using that at work. So while that case is probably the most complicated case of all the cases that I'm going to talk about today, it's the case that I don't feel is worth talking about as much because it hasn't really been pertinent to what we've been doing at work. So yeah, next I want to talk a little bit about the static lib. So if we go to static lib test, once again we have the same sort of setup. So we have static lib, and this one is going to look a little bit different if we look at the source code. So this is, once again, this is on Rust edition 2021, not 2024. So this doesn't have the unsafe no mangle that you might see in future code. So this is what the current edition expects, but previous editions of Rust didn't require that, because the whole unsafe story is changing on the regular, I would say. It's a ever-evolving story, but essentially this is the same sort of function that we had before, except this is extern C instead of just a pub fun. So this is using like the C ABI, and we have to have this no mangle. And if we look at the cargo.toml, we can see that the crate type is static lib. If we looked at the other crate type for dilib, it would have been just dilib, by the way. Forgot to show that off. But yeah, essentially, we can just do a cargo build here and see how that goes. One thing that you can also do, if you cargo build, you can use -verbose to see the exact command that was run. Now, if it's already built, like what I'm showing here, you won't see that. So you'll have to run a cargo clean. And then you can do a cargo build verbose. And then it'll actually show you the Rust C command that it uses. And this is actually really useful because, for instance, if we go back to dilib for a second here, I know I'm jumping around a little bit, but this is kind of important to understand. If we go back to dilib here, if we do a cargo clean, cargo build dash verbose, we can actually see when it's building the dilib lib, it's actually adding this prefer dynamic flag here, and this is actually really important for this dilib case in particular, because without prefer dynamic, it'll try to statically link its dependencies. And so what's going to happen is it's going to statically link, say like the standard library, for example, into the library, and then it's going to try and statically link the standard library into the binary. And then it's going to get confused because now there's two versions of the standard library and it doesn't know what to do. So if you're not using cargo, this is something you actually have to manually add when you're running Rust C to compile the library. But when you are using cargo, it actually is smart enough to add this in automatically. So that's kind of nice. Anyway, back to our regularly scheduled programming. So we were in the static lib here, and we were building this. I was just showing off the cargo build verbose flag. And if we come back out of here, so yeah, what's happening here is, sorry, let me go back in. What's happening here is we're actually building a .a file, and that's what I showed off a little bit earlier when I added static lib as a crate type to the rlib example. So if we look at this, we're actually getting just like a system.a library, and at least that's my understanding. And so this is kind of divorced from Rust itself. So once you start, exporting functions from Rust using extern C, using like the C ABI, that's when your output is basically, for all intents and purposes, just another C library, right? Like if you were to compile a C program as like a static library, this is the output you would get. And so if other languages like Java or Golang or Python need to consume this, then they just need to build an interface with C code. So this is kind of the standard use case for FFI. If you're trying to call foreign functions from other languages, then you would do it through the C ABI like this, and it makes things a lot easier. You'll notice that the binary size here is quite large. We'll talk about that in a moment. We're going to go over to the static lib bin. And on this side, we'll see that the code uses this extern C block to declare this add function, and then we're going to call it here. We need unsafe because whenever you're calling an external function, it's always unsafe. It's implicit here, but they actually make it explicit in the most recent edition of Rust. So if you're on Rust edition 2024, you need to explicitly add unsafe here, otherwise it doesn't compile. But before that, it was kind of known that, hey, if you're declaring an extern block like this, right, then, well, of course it's going to be unsafe to call functions that are defined in C or whatever other language, right? We don't actually know how those functions were written. We don't know if they're written in a memory-safe language or if they were, manipulating pointers correctly. So it's always going to be unsafe to just call into one of these foreign functions. So that's why that looks the way that does. What else do I want to show? Probably the cargo.toml. Cargo.toml has no dependencies, and that's because, like I said, this is not really tied to Rust in any way at this point. Like, once we've produced our library, for all we care, that library could have been produced by C or Go or some other language that produces .a files, right? So Cargo doesn't really have to be aware of that. There's no metadata that it can work with. So that doesn't really matter. And this is how you would be able to call, code from other languages from Rust as well, right? So now we're actually consuming the library from Rust. We don't know which language it's from, therefore there's no metadata specific to Rust that we can work with here. One thing that you should note is that when you're calling foreign functions from Rust code, you usually have this build script. So you set stuff like this rusty link search. Here I'm pointing it at static lib target debug. This is probably not a very portable solution, so if you want to use this on different operating systems, you probably don't want to do it this way, but this is how I'm doing it for the purposes of this demo. And this is going to set the -L flag, or sorry, -L flag for the linker, and this is going to set the -L lowercase, I believe. So you have to set, you have to say that it's static here. So you set static equals static lib underscore lib. We're going to see that it's going to look a little bit different when we work with the C dilib. But that's something that you have to be aware of if you want to be able to properly link your dependency. So if we run that, we can see that it says sum3. And if we go into the target debug folder, we can look at this binary here. And we can see that the binary size is significantly smaller now compared to the static library that we created earlier. And this is something that's actually really worth noting, is that your final executable is actually going to be a pretty reasonable size relative to the library, the static library that you're linking in. And that's something that we want to keep note of as we look at the dynamically linked library. So I'm going to pop my way back out of here. We're going to go into cdilib. So we're going to look at cdilib lib, and we're going to take a look at the code. And once again, the code looks exactly the same as what I showed off in the static lib case. So cdilib is basically like a C dynamic library. So that's when you want to export your functions through like the C ABI, for example. And thus, if we go to the other side, hang on, we should actually build this first. So we're going to do a cargo build. And then we're going to come to, oops, I went up a level too many. cdilib bin, wait, what am I doing? Too many CDs. We're going to look at the source here, and it's pretty much as you expect, no differences here. The cargo toml, also no dependencies, and the build rs looks pretty much the same. Obviously we're changing to cdilib lib instead of static lib, and same here. We're using dilib So that's the link type you need to use here instead of static. It's also not cdilib, notably, but it's dilib, and then you set it to cdilib_lib. And so, and the reason why it's cdilib_lib, by the way, is because if we build this, cdilib_lib. The reason why it's cdilib_lib is, I keep doing that. If we come back to this, I'm getting all mixed up. You'll see that the .so that we've created here is lib cdilib_lib. So the name that you want to provide is just this part without the lib prefix that's implicit. So whenever you use the -l flag and pass that to the linker, it automatically inserts this lib for you, so you never specify this lib prefix. It's a little bit confusing, among many other things that are very confusing about linking. But, oh yeah, another thing that we should look at before we leave this behind is the SO file. So this is the dynamic library, and you'll see that it's significantly smaller than the .a file that we produced. Remember, the .a file was, what, it was like, I don't know, was it like 11 million or something? I don't know, it was this big number here, right? But this one, comparably a lot smaller. It's about, I don't know, maybe 500K, right? So we're going to come to the cdilib bin here, and I think I've already shown off the code here, so I'm not going to do that again. And we're going to run this, and we're going to see, oh, hey, look, cannot open shared object file, no such file or directory. Isn't that weird? So one thing that you have to know to do when you're linking stuff is you need to set so for the dynamic libraries, it's a little bit weird, especially when you're working with relative paths. You have to set like an R path. I tried setting the R path for this through Rust-C through various different means. Like I tried passing in like linker flags in the cargo toml. None of that was working for me. The only thing that actually seemed to work was just doing like an export. Actually, I don't even have that here, do I? Never mind. We'll have to do it manually this time. So I had to do an LD library path equals, and then I just kind of took this path here, just copy that, paste that here, and you give it cdilib lib, and then we want to tell it where to look for the .so. That would be under target/debug. And so if we do this, now if we do a cargo build, we'll see that it actually succeeds. If we do a cargo run, this time it actually works. So that's something that's really important to understand. If we go to the target directory here, we can take a look at our binary. And we'll see that this one is also around 500K, a little bit over 500K. Now, you might be thinking, like, okay, the libso version was a lot smaller than the .a version, right? So isn't it always better to build the dynamic library? But there's kind of an important catch here, right? Because this is static linking versus dynamic linking. And this is something that kind of tripped us up, was we were producing, I think, .a files for Golang, because for some reason when working with Golang, it only seems to accept the static linking. That's more like a Go-related issue. I don't know exactly what was going on there, but it is kind of complicated. I'm sure that there are ways to do to link dynamic libraries in Golang, but anyway, that's sort of a tangent. But yeah, essentially, we were having issues trying to do dynamic linking in Go, and so we had to use .a files, but we were writing some other code in other languages, like in Java, and there we were able to just use the dynamically linked library, and that was totally fine. And so one thing I really wanted to point out is that if we go back to cdylib lib and we do a cargo clean, and we come back to cdylib bin, so cargo clean deletes the target directory, which means that we've deleted the library, the .so, from the system. So what do you think is going to happen when we try to run our binary? Well, if we do a cargo run here, we're going to see that, hey, look, we got that error again. It can't open the shared object file. But this time it's not because of the LD library path not being set. It's because that library doesn't exist on our system anymore. So this is kind of the catch, right? So if we look back at the size of the binary for the static linking, right? We'll see that it was about, just over 500K for the static lib bin. And so what's really interesting to me is that if you take the total size of the cdylib bin plus the SO that is required to actually run this, right? That's actually well over, that's like almost, like 1 million bytes, right? That's way larger than the final static library that we created. And just to prove it to you, I'm going to go and hop into the static lib test. We're going to go into static lib. We're going to do a cargo clean here. So now we've deleted the .a file that's wiped from our system. And if we go back to static lib bin and we run cargo run here, we're going to see that it still works just fine. And that's because that library has been statically linked into the final binary. So we don't actually have to worry about, this thing not working anymore just because we don't have that extra library file. And we don't have to worry about linking that in either at runtime, like what we do with the cdylib bin. So overall, at least from what it looks like to me, the static library actually ends up giving us a smaller executable size at the end of the day. The actual .a file was very, very large, right? But the compiled binary that we got for our executable that used that .a file ends up actually being smaller than the sum total of the shared library, the .so, plus the cdylib binary that executes using that cdylib library. So that's kind of interesting. So in this case, it looks like the static linking actually wins. And this is something that I think kind of tripped us up because, we're building our executable code on like the Golang side, right? So we're not really seeing it in this sort of lens where we're just taking it out and popping it open in another like small Rust executable and seeing what that looks like. And so I remember like one of our teammates was saying like, oh hey, like this, like what's going on? This like library size is huge. This .a file is massive. Like what's wrong with Rust? Why is it making these massive libraries? And maybe there is some issue there. You can turn on LTO, right, link time optimization. You can try and strip the binaries and stuff, but at the end of the day, it's still going to look relatively large. But yeah, if you see the end results when you actually compile those statically linked libraries into the executable binaries, you'll see that the final binary size is actually a lot smaller. It might not be as small as in other languages, right? Rust tends to favor runtime, like performance over space efficiency. So whenever it can make that trade-off of your code runs faster, but maybe it consumes a little bit more memory or a little bit more disk space, and that's usually the choice that Rust will make. Whereas, if you look at something like Swift, for example, how they achieved dynamic library linking, where Rust didn't by having like an actual stable ABI, they tend to make the opposite trade-off, where they look at reducing binary sizes at maybe a little bit of a performance hit, right? Or at least, that's what I've been told. That's what I've been told. I'm not going to state that I'm like the expert in all these things. I'm just, looking at various articles and trying things out and, witnessing stuff happening at work, on the job. And so, this is kind of the collection of things that I have noticed regarding linking, at least with respect to what we do at work with FFI and Rust. So, that's pretty much it. I'm going to take a quick break here and just check over my notes here. I'm probably going to just quickly edit this out. Okay, a couple of notes that I wanted to mention before I go here. There's a very, very helpful tool, LDD, that you can use when you're trying to debug linking errors. So if you use LDD on your output binary like so, you can see what it links to. This is the static linking. But if we look at, say, cdylib, so go to the cdylib bin, and target debug, and we're going to do an LDD on this one. We'll see that we can actually examine what it's linking to, and it says that it can't find this cdylib _lib.so. So this will already tell us that if we try to run this code, it's not going to work. So we can actually, there's another helpful command here called read elf-d, -d for dynamic, which apparently looks at like the dynamic section or something. I don't know. There's some documentation for that here. Displays the contents of the file's dynamic section if it has one. And this can also be helpful if you give that your cdylib bin, like so. So here we can actually look at the run path. I think Nix might do something funky with that. You can see it's pointing at like the Nix store here. But in other examples I've seen online, it actually prints out the R path. By the way, R path and run path are not the same thing, apparently. They are different things, but apparently R path has priority over run path, and then LD library path has priority after that, which is what I've been using, is the LD library path. But anyway, this is another thing you can look at that might be helpful for just kind of poking around and seeing like, if I see this shared library, where's the actual run path where it's searching for this stuff, or the R path rather. It wasn't super helpful for me here, but it seems like it helped other people, so it might help you. But yeah, LDD definitely is very helpful because that can just give you this not found and let you know immediately, like, hey, there's something wrong. You don't even have to try and like run this thing. So that's what you would use on Linux. Now, if you're like me and you started this project on a Mac, there's another tool you can use, otool -l, and then you give it your binary name. So in this case, it would be something like dylib-bin. I'm not going to execute it here because obviously that's not going to work. But that does something similar. That can kind of tell you, it won't necessarily tell you if it's not found, but it'll show you the path that it'll be looking for things in. And I found otool to be very helpful when I was debugging linking issues on Mac. If you're on Windows, good luck. I don't know anything about Windows and linking, so I can't really help you there. The other thing I will note is that on Mac, everything here just kind of worked out of the box. I didn't have to set any LD library path. I think that might be a Linux specific thing. I'm not really sure, but yeah, I didn't actually have to set that at all. I didn't have to set an R path. So the way that this is handled on Mac OS is just different, I guess. I don't really know why. It just magically works. Do we like magic? No, but when it works out, hey, we take it. So that's another thing to look out for, is portability concerns. That might be something to do with the fact that I was using relative paths here and not doing whatever you're supposed to do in your build scripts. Because, yeah, obviously we have custom build scripts for everything when we're building these binaries here. Now, of course, if you're calling your code, your library from Golang or Java or Python or whatever, then you're not going to have these build scripts because you're not going to be building a Rust executable. You're probably building a Golang executable, for example. But yeah, anyway, that's pretty much it. Thank you for listening. If you enjoyed this, then cool. I don't monetize this channel or anything, so I'm not going to ask for likes or subscriptions or whatever. So yeah, whatever. Peace.